Hello and welcome to Electrons Part 1, the basics. Electrons are pretty complicated, especially compared to protons and neutrons, since they can move around and exist outside the nucleus. So we're going to break them down into two separate topics. Mass of an electron is extremely small. They actually call it a negligible mass. For our purposes, especially this year, we are able to actually ignore it. It isn't actually a mass of zero. There is some mass there. It's just so small compared to the mass of a proton or neutron. It would take about 1,500 electrons to equal the mass of one proton or one neutron. The charge of an electron is -1. You probably remember that from some of your earlier science classes. As I mentioned before, electrons are located outside of the nucleus. We actually know now that they're located in something we call orbitals, which we briefly mentioned when we talked about atomic history. Originally, it was thought that they were actually in orbits, which are circular paths, but they're really in these orbitals, which are actually kind of like clouds or regions of probability of finding an electron. Electrons have a specific amount of energy. Energy is related to location for electrons, so every single electron has its own little location and its own individual little energy. What makes them a little bit different from protons and neutrons is that electrons can move. They can move around within the atom outside the nucleus, and they can also actually move from one atom to another. Again, electrons are located outside the nucleus in orbitals. These orbitals exist in things that we call principal energy levels, or PELs. So Bohr wasn't way off with the idea that electrons exist on energy levels. It's just within those energy levels are actually these more specific regions where electrons are kind of moving around that we call orbitals. PELs are like the rungs of a ladder. Electrons can only exist on specific energy levels. So if you were climbing up a ladder, you would actually have to stand on specific rungs. You can't simply step in between rungs, things like that, you'll fall. So electrons actually have to be right on these rungs. Those rungs are where orbitals exist. Now, electrons can move from one rung to another, and that actually involves an exchange of energy that we're going to talk more about. On the bottom of a ladder, you're at the spot where there's the least energy, meaning if you were to fall off the bottom of the ladder, it wouldn't hurt that bad. If you were to fall off the top of the ladder, it's going to hurt a lot, because you're going to have a lot more energy by the time you hit the ground. This is kind of analogous to what's going on inside of an atom. If you imagine that this is the nucleus down here, the further away from the nucleus, the greater the energy. So if you have an electron that's very far from the nucleus, it's a high energy electron, compared to one that's closer to the nucleus, which is a lower energy electron. In order to move from one rung of the ladder to another, electrons must either absorb or emit energy. So if an electron wants to go up to a higher energy level, it has to absorb energy. If it wants to move down to a lower rung, it has to emit or give away energy. So to absorb energy means gaining energy from the surroundings, whereas emitting is kind of like giving away. It's the idea of releasing energy to the surroundings. Remember, energy, we have this law of conservation of energy. It's not created or destroyed. It has to either be given away or converted to something else. So we're actually going to have two ways in class that we add energy to electrons. We can use electricity, we can use heat, and electrons will actually move up to higher energy levels. When they fall back down, they actually give off light. If you saw any cool fireworks displays over the summer, you saw evidence of this. So we'll talk about how that process occurs. And again, energy within the atom, as far as your proximity to the nucleus, closer you are to the nucleus, the lower the energy. Farther you are from the nucleus, the higher the energy. So it's very important to keep that in mind. Another thing that's really important to reiterate a little bit is that every single electron is in a slightly different place. No two electrons can be in the same place at once, just like no two people can. So every electron has its own individual energy. More electron configurations actually tell us the principal energy levels where different numbers of electrons exist. We use predominantly in reagents chemistry 4 electron configurations, but we will also look at quantum configurations as well. From your periodic table, if you take a look at any of the squares in the periodic table in that bottom left-hand corner, you will see the electron configuration in what's called Bohr configuration. In other words, you have your specific PELs just telling how many electrons are there. There is a more specific way in quantum configurations to tell that even within those principal energy levels, there's a little bit more detail that we just don't see in this configuration. It's not wrong, it's just not very detailed. So my Bohr configuration for arsenic, I have a first principal energy level, and remember that's going to be the lowest energy, and that's got 2 electrons in it. Take a minute and you look around on the periodic table, you're going to notice that no first principal energy level has more than 2 electrons in it. On some of the larger atoms, I know some of you guys might be looking at those and you're like, hey, it starts with a bigger number. It actually starts with a little dash. There's a 2-8 they took out there. Second principal energy level in arsenic is holding 8 electrons. If you look around in the periodic table, that's the most the second principal energy level can hold. The third PEL for arsenic is full with 18 valence electrons. And last but not least, we have this last number in the configuration. It happens to be our 4th principal energy level for arsenic. And our outermost electrons, okay, remember these are our higher energy electrons over here. Our very outermost ring, whenever we're looking at a particular atom, is something we call our valence shell. So the valence shell doesn't have to be the 4th PEL. It really depends on the particular atom that we're talking about. The last number in the configuration actually tells us our valence electrons. Those are really important because they predict chemical behavior. So again, valence electrons are outermost electrons in an atom. They're in the highest principal energy level that that atom has. These are the electrons that would be involved in bonding. They can actually be gained, lost, or shared. If you look at group 18, you're going to notice something about all of their electron configurations, well, except for just one. You're going to notice that they all, with the exception of helium, actually end in 8. Helium's just too small, so it's okay for it to end in 2. So if we look at group 18, we'll notice that they all end in 8. 8's a pretty cool number in chemistry. It's actually kind of a cool number in music, too, if you think about octaves being every 8 notes. Everybody in group 18 has 8 valence electrons. And that actually is kind of why we call them noble gases and contributes to their behavior. If you look at group 2, everybody's got 2 valence electrons. A lot of the groups show these properties. It's a little bit weird in the middle of the periodic table, but your groups on the edges tend to show those similarities. Lewis dot structures are structures that show only valence electrons. So these can be very, very helpful to us because Lewis dot structures are very important because they only show valence electrons, which are bonding electrons. So Lewis dot structures are a nice way to summarize how we predict atoms will bond. Drawing the Lewis dot structure is pretty straightforward. You first write the symbol for the element, and then you're looking at the electron configuration. And when you're looking at the electron configuration, you see how many valence electrons there. We actually ignore all of the inner electrons. We'll also draw Bohr configurations. These show all the electrons. They're useful sometimes, but Lewis dot structures are pretty straightforward and work for when we want to talk about behavior of an element or bonding. Then we draw those dots to represent electrons. We like to keep them kind of generally in pairs whenever possible, or pretty symmetrical if possible. So the first one we're going to do is sodium. So you're going to start by writing sodium's formula, or sodium symbol, which is Na, not S. And you're going to find Na on the periodic table. So you're going to go ahead, and you're going to write Na, and you're going to find it on the periodic table. If If you look at sodium's configuration, it's 2, 8, 1. Sodium has 1 valence electron, and that's the only electron that we actually care about in a Lewis dot structure. Boom, we're done. So I'll show you my nice little typed pre-made sodium. There it is. So aluminum, you're going to write down your symbol for aluminum. Find the configuration on the periodic table. We're going to have 3 valence electrons. Now what's important here is you can't put all the 3 on one side. So you're not allowed to do this. That's not allowed. If your dots don't look exactly like mine, say you did this, or say you did that. It doesn't matter. That's fine. What's really important here is that we want to make sure that we don't have more than 2 dots on any one side of our aluminum diagram. I tend to kind of lay them out where I have more of them on the right, and I like them in pairs because electrons actually exist in pairs. Take a moment and do chlorine. So for chlorine, you should have had 7 dots, sorry. So you have 1 missing spot. And again, if you had drawn this instead, that's totally fine. You have 7 dots, no more than 2 on any one side. Again, valence electrons are extremely important because they determine things like chemical properties. So, we haven't really talked a lot about chemical and physical properties in this particular unit, but it's nice to be able to kind of make some comparisons here. So if I look at some group 1 elements versus some group 2 elements. So sodium and potassium have the same dot structure. They both have 1 dot. If we look at their boiling points, their densities, and what's called their bonding ratio. So melting point and density are both physical properties. Our melting points are pretty close. They're not very far apart at all. Those are in Kelvin. And I actually just looked those up on the reference table. Densities I looked up on the reference table also, those are really close as well. So I'm seeing some pretty similar physical properties. Bonding ratios are a chemical property. What this means is how many sodiums bond with a chlorine. So sodium and chlorine bond in a 1-to-1 ratio. Sodium, potassium, and chlorine. And when we get more into bonding, we'll talk about why that is. But let's compare this. All I'm really looking for here is comparison to magnesium and calcium, which each have 2 valence electrons. So they have 2 dots in their dot structures. You're going to notice their physical properties are different from sodium and potassium. So if we look at these 2 numbers, they're still relatively close compared to these 2 numbers, which are far away from those. Our densities are also pretty close. So notice that physical properties actually have some relationship to things like location on the periodic table. This is actually extremely important in chemical properties. We also all of a sudden notice that the bonding ratio changes here because of those 2 valence electrons. And again, we'll talk more about why that actually occurs later. What's important today is understanding how to draw a Lewis dot structure and